Okay, here we're going to look at an example of a standing wave. Now, unlike a traveling wave, a standing wave never really goes anywhere. It merely oscillates up and down within the medium itself. And in this case, our medium is simply a string that is being pulled across the table here. It's held by a weight on one side and it's attached to a thing that will oscillate the string up and down based on a certain frequency. Now, as you can see, not much is really happening here. But every string has what's called a fundamental frequency for a standing wave. It's the lowest sort of frequency that it can actually reach, with also the longest wavelength. In this case, the frequency is around 4.6 hertz. Now, that's the lowest frequency. Now, that is actually based on a combination of things: the mass of the string, the length of the string, and the amount of tension that is placed on the string. So those three things affect what your lowest frequency is going to be. But also we know it's the lowest frequency because there is what's called a single antinode. And an antinode is this center area here where it is oscillating the most. Now, in addition, there are two what are called nodes, fixed points at either end where there are no oscillations. So standing waves have these combinations of nodes and antinodes. And what we have here is actually only one half of a wave, okay, because there is only that one antinode. Now, let's double the frequency. And we're going to do that by changing the rate at which the string is oscillated, the frequency. So let's do that. So now I've basically doubled the frequency. Now, as you can see, by doubling the frequency, there are now two antinodes and a singular node here in the middle. And now I have one full wave that is in there. So now the length of the string has not changed. So by doubling the frequency, I have cut the wavelength in half. And again, that relates to the idea that the wave velocity is constant. So no matter what I do to that frequency generator, the velocity at which it vibrates actually always remains the same. So by doubling the frequency, I have cut the wavelength in half. And now I have three nodes and two antinodes. So now let's triple the original frequency. Now remember, the original frequency was around 4.6 hertz, so let's triple it. So by tripling the frequency, now I have three antinodes. Okay? And these doubling, tripling, anything like that are known as the harmonics of a standing wave. I can't change the length, I'm not changing the tension, anything like that. But again, by tripling the frequency, I've now cut the original wavelength by 1/3. There are now three antinodes and there are four nodes. So one more time, let's quadruple it. The fundamental frequency has been multiplied by a factor of 4. Now as you can see, there are now 4 antinodes and 5 nodes. The wave is oscillating very fast, so it's sometimes kind of hard to see what's really going on. So let's put it under a strobe light and see what a standing wave looks like now. Now, the way we see things is actually via reflection most of the time. So light is coming off the strobe light, bouncing off the string and coming to our eyes. Now the strobe light flashes at a certain rate, so we actually see the string at different moments because of how fast the strobe is flashing versus how fast the string is actually moving. So if we adjust the flash rate, it suddenly appears to change the motion of the string, but the string's motion has not changed at all, just the rate at which the light bounces off the string and hits our eyes. So the closer we get to matching the actual frequency of the string, now you can more clearly see that true standing wave as it oscillates back and forth, okay, and that it actually forms these patterns here. So that if we can hit the actual frequency, which you remember was 18.6 hertz, it appears that the string is now frozen in time, but that's because the rate of flash of the light perfectly matches the frequency of the string's oscillation. And so the light is bouncing off the string at the same moment the string is in this position every time, giving it the illusion that it is sort of frozen in space. Okay? So that's basically what a standing wave is. A wave that simply oscillates up and down within the medium. It does not travel back and forth. it forms these nodes, areas of no motion, and antinodes, areas of maximum motion.